Okay, this is College Algebra Chapter 2, Section 3 on functions. So literally we're going to start out with what I always think is the easiest definition in all of mathematics. As you get better and better at mathematics, not just doing algebraic manipulations, you will soon learn the heart of mathematics is the definitions. And when you're asked to do mathematical reasoning, you always start with the given definition. We try to make them as precise as possible. And here is the easiest mathematical definition you'll ever get. So a relation, so that's what's being defined, the word in bold, is a set of ordered pairs. That's it, done. That's the definition. So you're probably used to sets like this. You start when sets are small and we can list their elements, we can write them like that. And this set has 4 elements. Remember, sets are not ordered. I can change the order of the elements in any way I want, and I've not changed the set. And when we do it in set lister notation, I just simply separate each element by a comma. But this may lead you to think that sets contain real numbers. But that's not what a relation is. A relation is a set. So the very first thing we have to know about a relation is a set. And what are its elements? Ordered pairs, like 1 and 7, 0 and minus 8, 4 and 22. This is a relation. We could call this relation, we could call this set relation 1 if we wanted to. So that's as simple as it is. I'm actually given the exact definition. Sometimes we say, well, we don't want the set to be empty, and we'll say a relation is a non-empty set of ordered pairs, but it doesn't make any difference for this class. In a mathematics class, if you were actually math majors, it would, because we have to take care of things known as trivial cases. That requires that you have just a little bit of logic under your belt. So here we have some other concepts. So let's just go with this right here. So this is my relation right here. So every relation has a domain. And let's write the domain of R1. So that's the domain of this relation. Well, it's the set of all of the x values. So the domain of this relation, since the relation is so small, R1, we can just identify all of the x values. That's the first coordinates. And hence, the domain of R1 is 1, 0, and 4. I know I have extra space over here, but I was overly ambitious in writing the set. So notice the domain of a relation is the set of all x values. Now I'm going to get a little bit technical here, and for the most part you can ignore it. And as soon as I say you can ignore something, you probably actually literally do. But literally, the domain of a relation R it's a set. It's the x values such that x, y are in R. So that's literally what it is. So what this says is this is a set. The set contains x values such that those x values are in the ordered pairs contained in R. And here is a specific example of a domain of R1 where R1 is defined and it's small. The reason I bothered to show you this is because most of our relations are going to have an infinite number of elements in them. So again, this is element, this is an element, meaning this, this, and this. This only has 3 elements in it. But many of our relations will have an infinite number of elements in it. So I can't just simply list the domain. I have to actually do it another way. And this is called set builder notation. This is called set listing notation. Set listing notation works if there's just very few elements in the set and you can list them all. Usually the sets are infinite or much larger than what we care to list. So the range, let's do the range. The range of a relation is the set of all y values. So right there is my relation, and let's find the range. The range of R1. Well, I take all of the y values. So I look at each ordered pair, and I grab the y value. Second ordered pair, minus 8 and 22. So I almost hope that you can see what's coming over here. So the formal definition of the range of a relation is going to be the following. The range of a relation R, I'm giving it a name R just because it's easier to refer to it, it's a set of y values such that x, y are in R. So that's the formal set theoretic or set definition of a range, and this is the formal set definition of a domain. Domain of what? R. Notice here x always stands for real numbers, y always stands for real numbers. So here is a little bit of something I might want to point out. I always like that because it's an eyeball and it's a nose and you're looking at something, and it also means I in Spanish, and it's also what you use in Spanish if you want to call attention to something, ojo, and you see it actually written on pieces of paper. So when we're talking about ordered pairs x, y, the things that you graphed, then x and y are, for your class, real numbers. They have no imaginary part whatsoever. They're not complex numbers with an imaginary part. So that's, sometimes I don't even need to say that, but I was kind of looking ahead, and I think maybe it would be a good idea now to talk about that. Now in advanced mathematics we don't necessarily make that restriction, but for you guys we do, because we want to graph something and we only have a two-dimensional graph. How would we graph something in the form a plus bi, c plus di? Wow, how are you going to graph that? Because this requires 2 bits of information, and this requires 2 bits of information. That's 4 different axes, and we only have at most 3 in the 3-dimensional world. So it becomes difficult, and it's fascinating, the answer to that question. It's something that you'll never deal with unless you take a complex variables class, and you would only take that if you were a math major. So here is the next question. Let's just go on down the list. So I start out with a bunch of definitions. So a function now, it's a special type of a relation. Just like a cow is a special type of a mammal, and a mammal is a special type of an animal. Not every mammal is a cow, just like not every relation is a function. But every cow is a mammal, so every function is a relation. So a function is a special type of a relation. What makes it special? For each distinct value of the first coordinate of the ordered pair, there is exactly 1 value of the second coordinate. So it's kind of hard to visualize. Don't worry, we'll see a lot of visualization of this. So let's look at some other definitions that are equivalent of a function. A function is a set of ordered pairs in which no first component element is repeated. So for example, I'll give you an example of a not a function. Not a function, but a relation. So a mammal, but not a cow. 5 and 7, and 5 and 0. This is a relation. Why? Because it's a set of ordered pairs. But it's not a function because a function is a set of ordered pairs where no first component is repeated. Well, here I have a 5, and here I have a 5. So the x value is repeated. So this is not a function. And another definition of a function is a rule that assigns exactly one range value to each domain value. So this is assigning two range values, right? The range value of 7 is assigned to 5, and the range value of 0 is assigned to 5. Well, that can't happen if you have a function. So now we have some tests. Let's see which of the following are functions. Now, if we look at f and g and h, they're all sets of ordered pairs. So f, g, and h are all relations. So what we want to do is check to see if they're functions. So they're really small. I mean, f is a set of 3 ordered pairs, g is a set of 4 ordered pairs, and h is a set of 3 ordered pairs. So they're easy. So we just visually check. 1 is not repeated, minus 2 is not repeated, 3 is not repeated. So f is a function. Oh, g is not, because 1 is repeated 3 different times. It doesn't matter that it's 3 different times. All I need is the repeat of an x value to happen once. So g is a relation, but not a function. Number h, we have a minus 2 repeated twice, so h is a relation, but not a function. So let's go on and do example A in objective 2. So here we have, and then I'm just going to leave it up here written and write down here. So finding domains and ranges. So we'll actually call this relation A. That's an appropriate name to call it. So the domain of A is, well, it's a set. Go back to the definition. It's a set. It's going to be a small set of all of the first element values. So 3 is in there. 4 is in there. Oh, do I need to write 4 again? No, I don't. Because a set is defined by its elements. If I were to add 4 in here, it's not that that would be improper, it's just not common. It would not change the set. It doesn't change anything because 4 is already in there. So we don't add 4 again if we've already got it in there, and we'll get a 6. So that's the domain of A. So let's find the range of A. And again, it's going to be a set. And it's going to be minus 1 is going to be in there. 2 is in there. 5. And 8. So notice that there's more elements in the range than there is in the domain. That's okay. What we cannot have is just the reverse. There cannot be more elements in the domain than in the range and it be a function. So let's go ahead and do the same thing for B, although pause right now and do it yourself. So I'm doing the range first, 2, and that's it. So there's only one element in the range of B. What about the domain of B? Remember, I did the range first. Well, we have a -5 and a 0 and a 5. So again, we have more elements in our domain than in our range, and that's perfectly fine. But up here, we have more elements in the range than in the domain, and I'm saying that's okay. This is A is, let me take that back. That's not okay, because if we want, let me disambiguate that. It's okay in general for that to happen, but it's not okay if we want the relation to be a function. And that's the important thing. So it's okay that the domain actually has fewer elements than the range when we're talking about relations. But it's not okay if we want the relation to be a function. As you can clearly see here, we have 2 values of 4 repeated. So the relation A is not a function, but the relation B is a function. And I think maybe just leaving it at that and looking at some visual examples will be more helpful. So now we have some graphs. So we've got to decide how to define the domain and the range of relations from graphs. So here I have 1, 2, 3, I got 4 different graphs. And for our first graph, we want to find the domain of A. Well, this is simple. Our relation is -1, 1, 1, 2. Notice how they've got the different colors for the x value and the y value. Now, there's no claim that this is a function. It's a domain, and we can talk about the domain of this relation. So the domain of A, so this is A right here, is going to be no longer ordered pairs, and the range of A, so this right here is A, is again, it's a set of the second elements. So A is pretty much taken care of. If you were just given points right here and not the values, not the coordinate values that correspond to them, you would have to figure out what is the ordered pair that corresponds to this point. You go over 1, so that's the x value. You go up 2, so it's +2. To this point over here, I go to the left from the origin 1, so that becomes -1, and up in the positive direction, so it's +1. Down here, I start at the x value at 0 and go down -1. Over here, I start at an x value of 1, 2, 3, 4, and then go down -3. And then you could just literally write out the relation and then extract the domain and the range. We can't do that over here. We can't do that at all. So let me bring up Geogebra. I should have done it before this class started. So this is every point. So this is the graph of a function. It's actually an ellipse, and those are the foci, but you don't have to worry about that. So here's what I want you to do. You've got to somehow figure out the domain and the range from this graph. So the domain. Can I move this over? Let me get this up. Get some writing area here. So the domain, I lost one of my icons. I'll get everything situated eventually, people. So this is what I want you to think of. The first off is when you're given a graph, think of domain. The idea that should come in your head is the x-axis. So here's the context. You're given a graph. Here's the graph. And from that graph you have to extract the domain. So imagine you are an ant. Well, I don't know. Imagine you are whatever, and you're walking along the x-axis. So any point, this is a really informal definition, but it always works, on the x-axis, where, since you're on the x-axis, you can look up or down and see a portion of the graph, then that x value is in the domain. So we're also imagining that you can see an infinite distance away instantaneously. So here we are, an ant, we're walking across down the x-axis. I'm looking up and I'm looking down, I can't see anything. So you're looking straight up and straight down, not at an angle. So I get right here to -7 and I look up, and wow, we're going to pretend that that actually intersects or touches the -7 line. Oh wow, I actually can see part of the graph of the ellipse. So that means I'm starting at -7, and then normally we want to include the endpoints, I believe. Let's include the endpoint. Let's just pretend it touches there. So I can start seeing it starting at -7. I'm looking up, looking up, looking up. I can see it up above me or down below me. So I get to this point right here. I can no longer see values below me, but if I scooch on over a little bit and I'm looking up, I can still see it. So I can literally still see a portion of the graph when I get to 2. So that's the domain of this graph. This is the domain of that graph up there. So now let's do the same thing with the range. Range, think of y-axis, and then looking to, in this case, not up or down, straight to the right or straight to the left. And any time you see any portion of the graph, then that's included in the domain. So we're starting up here. Well, just move this over. So here we are. We're starting up here. I'm going up and I'm walking down the y-axis, and about right here is when I can look to my left and see a portion of the graph. So that's going to be, let's just say, at 6.9. We're just kind of guessing. Now I'm walking down, I can look left or right and see a portion of the graph. see a portion of the graph. When I get to this point right here, if I look to my right, I can't see the graph anymore, but I can still see the graph if I look to the left, and that's all that matters. Until I get it 2, I can still see it in just a little scooch past minus 2. I said 2, I should have said minus 2. A little scooch past minus 2, we will say minus 2.1. I've got it, but this is wrong interval notation. I have to start at my negative value first and then go to my positive value. And we're just going to include the endpoints here, and that would be the range. Okay, so with that in mind, let's go back to our given exercises. So here we're walking. Let's do the domain value. You can see it's minus 4 to 4. The range value, I guess we should start from the negatives and go up, because we started from the left and we walked to the right. We should start from the bottom and walk up. We start seeing the graph at minus 6 until we hit 6. Over here, when you see these little bitty arrows at the end of a line, no matter where I am on the x-axis, if I look up or I look down, I'm going to see a part of the line because it goes on forever and ever. It's slanted. So that means the domain of this line is minus infinity to infinity. And when I'm doing the same here, again starting here, now if I look over, this line will be extended down. I'm going to see part of the line. The line gets further and further away from my y-axis as I go, but it doesn't matter. We're assuming you can see till infinity. So the range here is going to be minus infinity to infinity. So here's a hint. For lines that have a positive or negative slope, the range is always minus infinity to infinity. I'll start with the domain first. The domain is always the entire real line, minus infinity to infinity, and the range is minus infinity to infinity. Over here, let's do the range. Well, we'll do the domain first. Notice that, let me bring up a lot of people they don't know what to do with, because they literally stop graphing right there. But notice these two little points are going off in a slanted way. That means this parabola is opening up and getting wider and wider and wider. So that means that no matter where I walk on the x-axis, I'm going to be either able to see a parabola, part of the graph below, in between these 2 points right here, or over here, if I look up far enough, I'm going to eventually see the graph. So the domain of the parabola is minus infinity to infinity. The range, however, how do I find the range? I find if the parabola opens up, I go to the bottom point right down there, the lowest point, I walk over to the right or to the left, intersect my y-axis, and that value right there from minus 3 to infinity would be the graph. On the other hand, if I had the graph of a parabola that looks like this, not minus x to the 22nd, minus x squared minus 20. How is that? There we go. Now I have a parabola that is opening downward. So again, the domain of a parabola is minus infinity to infinity. How do you know the parabola? Its highest degree term is a degree 2 term. How do I find the range? I go to the topmost point, and I find where that topmost point intersects the y-axis. Here I made it really simple because I made that point literally at the intersection. So this was, the range is minus infinity because we start down here, we're going up. So I'm able to see it either side for no matter how far I go down. So I'm seeing it, starting from minus infinity all the way up here. I get to minus 20 and I can't see it anymore. So it's minus infinity, comma, to minus 20. That would be the range. Just take some getting used to and some imagination. Just remember, the graph doesn't stop right there. They just, by those arrows, they're assuming you can imagine it continuing on that way forever. So here are just some little bitty housekeeping things. So this is the underlying assumption. For most of you, this will not matter unless you're a really logical thinker. It might matter. We will assume the domain of a relation is any real number that when substituted for the independent variable, that's the x variable, gives a real number value. So that means if I can plug in any number whatsoever, I'm going to give you an example of this. It is kind of important. So I'm going to give you a relation that's also going to be a function. F of x, sorry, getting ahead of myself. It's going to be defined by a rule. Y is equal to the square root of x. So if I look at the graph of that, let's look at the graph of that. Point 5. We're going to see this. That's the relation. So the domain literally starts at 0 and continues on. The domain literally starts at 0. Why is that? Because we have to have real number inputs and outputs. So if I say if values less than 0 are included, and I say y is equal to the square root of minus 5, well, you should know by now that's the same as the square root of 5i. This is a complex number with non-zero component I, imaginary component, because right there's the I. So we can't have that. I can't plot that. That was the whole point. We have to have real numbers. So this particular relation would be characterized by x, and what is my y? It's the square root of x. Remember, any ordered pair is x comma y, but in this case I have stated that y is equal to the square root of x. So the domain can include 0, because the square root of 0 is 0, and any positive number. So the domain of that function, that was way lighter than I wanted to, the domain of this relation, which is actually also a function, is that. So let's go back. So that was rather important. The vertical line test. So this is a beautiful thing. You'll use it a million times. Isn't there an easier way to determine if I'm given the graph of a function? So if I'm given the graph of a relation, whether I can determine whether that relation is a function. So let me say that over again. You're given a graph of a relation. It's a set of ordered pairs, oftentimes an infinite set of ordered pairs. Is there any way I can determine visually, because I'm looking visually at the graph, whether it is a function? And we have a test. So given the graph of a relation, if any vertical line drawn on the graph, any, all you need is one, intercepts the graph just once. So this is, sometimes I will define this negatively, and I will give you the negative definition, but this is the positive definition, so let me read that, putting the emphasis on the right words. Given the graph of a relation, if any arbitrary vertical line drawn on the graph intercepts the graph just once, then the graph is the graph of a function. So let me give you an equivalent definition. It's easier to use. It's equivalent to what I just said, but it stresses how to find out if it's not a function. A graph of a relation is, here's the operant word, not. That's what differs. This is a test to see whether it is not versus whether it is not a function. A graph of relation is not a function if there exists at least one vertical line that intersects the graph more than once. So it could be twice, 3 times, 100 times, more than once. And I'm going to suggest that this is actually the test in the definition you use. Just remember, we're testing to see if it's not a function. So let me just do this right here. Just using the tools at my disposal, I'm going to draw a little pretend Cartesian coordinate system. And of course you remember this is always going to be the y-axis. This is going to be the x-axis. And here I'm going to draw. Okay, I won't draw it in the same color. I'll draw it in a different color. So there's the graph of a relation, clearly. Is it a function? So what we want to do is we want to draw some vertical lines. So I'm drawing a vertical line right there. It doesn't intercept the graph more than once. And I'm drawing one over here. And it doesn't intercept the graph more than once. But that doesn't matter, because it says if there exists at least one vertical line that intercepts the graph more than once, and right here I drew one, it intercepts the graph right there and right there, so that's twice, then the given relation is not a function. I think that's a much easier test. The definition I give here is, I'm sure, the exact one they give in the book. So use the vertical line test to determine whether the graph of each relation given in example 3 is the graph of a function. So here, let's just draw a vertical line through that point. Doesn't intercept another point. So remember, the graph of this relation is just the points. So I'm drawing a vertical line through the point minus 1, 1. It does not intercept another point. Here, the y-axis is my vertical line. It does not intercept another point. Here I'm drawing a vertical line at x equals to 1. It doesn't intercept another point. And here I'm drawing a vertical line. So, no. This is definitely a function because there does not exist any vertical line I can draw anywhere that will intercept this graph twice. What about over here? Oh, there's all kinds of vertical lines I can draw that's going to intercept this graph twice. So this is not a function. So A is a function. So A is a function. B is not a function. Drawing vertical lines here. No matter where I draw them, it's not going to intercept this slanted straight line more than once. So this is a function. And over here, no matter where I draw my vertical line, it's not going to intercept it, the graph, more than once. So this is also a function. So let's do the next objective. So the easiest way to determine each one of these is to determine what the graph looks like. And I want this to minimize in such a way that I can grab it. So let's look at y is equal to x plus 4. So the graph of y, this is 5a, y is equal to x plus 4. You should know this is linear. Indeed, if I were to graph it over here, I know that its slope is y, is it? No, it's not turning off that. Sometimes computers don't do what you want them to do. Is it because I've got my hand on it? Y is equal to mx plus b. M is the slope. The point 0b is the intercept. So the slope here is 1. M is equal to 1 over 1. And 0, 4 is the intercept. So I'm just going to pretend this point is 0, 4. And I'm going to draw a line through it. Not quite a one-to-one slope, but it's close enough for us. And, well, there's the graph. Is this a function or not? Think about the vertical line test. Start drawing vertical lines. Is there any place I can draw a vertical line on this graph so that will intersect this slanted line more than once? And the answer is no. So the conclusion is 5a is a function. And here is a clue. I'm going to give you a little box here. A little side note. And you should be able to conceptually think this through. Any line which has positive or negative slope is a function. And remember, if the slope of the line, if the line slopes up this way, this is positive slope because you're going uphill if you're an ant walking from left to right. On the other hand, if it goes downhill, then that is negative slope. So any line which has positive or negative slope is a function. You can take that as a theorem. I'm not going to prove it for you, but that's a theorem. So let's go on and let's look at number D. That's an interesting one because it's not an equality. All of these are equalities. So let's go and let's look at number B. Let's just do these in turn. The theorem I just wrote down will be used later on. So first let's find our relation is y is equal to 5b. Y is equal to the square root of 2x minus 1. So let's actually find the domain of this relation. So the domain. So remember, domains and ranges also refer to relations. And of course, since functions are relations, they refer to functions too. So the domain requires what? 2x minus 1 to be greater than or equal to 0. So let's solve this inequality. Why do I need 2x minus 1 to be greater than or equal to 0? Because if it's less than 0, this is a complex number. And these are real valued domains, real valued relations and functions. So let's solve this inequality. That means 2x is greater than or equal to 1. Divide both sides through by 2. That gives me x is greater than or equal to 1. So the domain is 1 to infinity. So let's actually try to plot this out. This is what you would do here. I don't really know what you would do, being at home and all. Well, I clearly, x has to be greater than or equal to, sorry, I forgot to divide through by 2. I'll eventually catch not writing things down because I eventually come back to it and I realize, there we go. So I just forgot, I said we'll divide by 2 and then I forgot to write it down. So the domain is 1/2 to infinity. So let's let x be 1/2 and our point y, 2 times 1/2 is 1, 1 minus 1 is 0, and the square root of 0 is 0. So I have 1 point on the graph, 1/2 and 0. The point here is you're not supposed to be using calculators. I know if you got a calculator, taking square roots is no problem. But I want my next number for x to satisfy what is my next perfect square. Well, the square root of 1 is 1, so I want 2x minus 1 to equal 1. So that implies 2x is equal to 2, so x is equal to 1. So I'm going to take my x to be equal to 1, then 2x minus 1 is 2 minus 1, which is 1, and the square root of 1 is 1. So I got another point. So this point is 1/2 and 0, and the next point is 1 and 1. Let's do one other. What are perfect squares? Let me get some more. Perfect squares. These are all numbers whose square roots are also integers. Can you tell me what the next one is? The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. So the next number will be 25. 36. In other words, these numbers correspond to 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So I've taken care of 0 and 1. I want to find some other points. So let's actually require 2x minus 1 to be equal to 4. So I solve 2x is equal to 5. X is equal to 5/2. And when x is equal to 5/2, 2x minus 1 is equal to 4, and the square root of 4 is 2. And you could go on that way until you get about 4 points. And what you're going to see is the following. Let's just go to Geogebra and take a look at it, because it does a much better job. We're going to see the following. Y is equal to 2x minus 1 raised to the, and there we go. So you see, this is the function. We start right there. The domain starts at 1/2. That's 1/2 right there. There's 1, so that's halfway between 1 and 2, and goes on forever and ever. So by looking at the graph, you can immediately tell, oh, this is a function. So it's a function. So our answer to number B is it's a function. And how do we tell it? We graphed it. What about this one? Y squared is equal to x. Y squared is equal to x. So let's use the square root property here. It's the only thing about, I can't change the bar colors of this program, and I wish I could. And it's really, really dark, and it's hard for me to see where to grab the bar to move it. So number C, we have y squared is equal to x. Well, normally we have y is equal to something in terms of x, right? In terms of x. So let me talk about this right now. So when we have the Cartesian plane, not that one, the x value are the independent variable. That's equal to x, and those are the domain values. So that's independent. The dependent value are y. Y values are dependent because they depend upon the x value. So what I need to do here is solve for y. So let's do it, and we're going to use the square root principle. And we all know it because it was on our last exam. I'm going to take the square root of both sides. And remember, the square root of y squared is y is equal to plus or minus the square root of x. Well, we kind of know what the square root of x will look like, but it's going to be plus or minus the square root of x. So if I take the positive square root of x, and here I'm going to try to just wing it, it's going to look something like this. But I'm also taking the negative values too, so I have to come down here and it's going to look something like that. It's kind of like a parabola but on its side, and since I'm taking both the positive and negative values, then it's not going to pass the vertical line test. So because of its graph, and because I took the plus and the negative values, by using the square root principle to solve for y, we discover that number C is not a function. So y, number A, that's a function, it's linear. Y is equal to the positive square root, so as we saw by its graph, that is a function. This is not a function, and now we have this weird one right here. Let's do this one. This is a good review. Whoops. So let me draw a Cartesian plane here. We're going to use it. So those are the plane, and then I'll plot things using a different color. And we have to solve y is less than or equal to x minus 1. Well, how do we graph this? So from intermediate algebra, what we do is we change the equation. So we change the inequality to an equation. So notice number D is an inequality. So we're going to change it to an equation. This is equal to y is equal to mx plus b. So the slope m is equal to 1, and the intercept is 0b, which is equal to 0 minus 1. So I'm just going to say this is 0 minus 1. The slope is 1 to 1. And we're just going to pretend that's a 1-to-1 slope. It's really not. It's a terrible 1-to-1 slope. That's much better. So right here is the graph of the line. The line. So if this is kind of a review, to graph inequalities, since this is less than or equal, we just graph the line and so this is the inequality. And we started to graph the inequality by choosing to graph the line. So that separates, so this is the line, y is equal to x minus 1. So now we want to know what ordered pairs x, y make this inequality true. So what we do is we choose a test point. So here comes our test point, and we get to choose it. And I always tell students, look where the line goes. You have to choose a test point somewhere on one side of the line, because as you can see, this line divides the Cartesian plane into two halves. So what I want to know is which half makes the original inequality true. So since the line does not go through the origin, I'm going to choose my test point to be 0, 0. So then you go back up to the original inequality, and I plug in the test point values. So remember, this is x, y. So y is 0, and x is 0. So is 0 less than minus 1? And the answer is no. 0 is greater than minus 1. So that tells me that my test point, which is right here, does not satisfy the original inequality. So what that means is nothing on this side of the line satisfies it. So all of the points that make it true are on this side of the line. And what we do is we shade it all in. And the points that are actually on the line, I'm trying to shade here. I don't have a shade function. I do, but I can't use it. And what would happen if I did? Nothing. It can't find a boundary. Oh, it did find a boundary. It was everything, right? Sorry, people. Okay, there we are. So basically, here's the point. All of this area is shaded, all of it. So if I draw a vertical line here, it's going to intersect the graph in just a million, infinite number of points. So what is the conclusion? Intersects the graph more than once? Not a function. In general, linear inequalities are not functions. So function notation. When a function f is defined with a mathematical rule, formula, or equation, we write y is equal to f of x. So here's the thing. If you see f of x, then you already know it's a function. You don't, because we won't use that notation unless we have already verified that it's a function. Now, of course, if you're wondering if someone's mathematical skills are good, you'd have to check. But in this book, we've already verified we will only use that notation when the relation is a function. So we write y is equal to f enclosed. So this is called f of x. F of x. In this case, the input value, which is the x value, are elements of the domain, and those are called the independent variable. And the output value is y, and that indicates a range value, and the y variable is known as the dependent variable. So keep that in mind. So recall this. Always keep this in mind. Y is equal to f of x. So when you see f of x, if you need to somehow replace it for y, so you can't be given y and say, well, that's equal to f of x. But if you already know that something is a function and you're given that it's f of x, then you can also say, oh, well, that's equal to y. So So that means ordered pairs taken from function. Every ordered pair is x comma y. But in this case, because y is equal to f of x, we can write them this way, x comma f of x. So let's get an example here. If y is equal to 2x plus 3, that's a linear function, and its slope is positive. The graph passes the vertical line test, so this is a function. So I can literally, I know already that this is a relation, and I just discovered it's also a function, so that justifies me to write that. So to evaluate the function, that means to plug in a specific value of x, we're going to evaluate it at x equals 2, we literally replace x with what it's equal to. So f of x becomes f of 2, because I replaced x with 2, is equal to 2. This is shorthand for 2 times x, so that's shorthand from 2 times x plus 3. Well, 2 times 2 is 4, 4 plus 3 is equal to 7. So we write f of 2 is equal to 7. Remember, 2 is the x value, and f of 2 is the y value. So that means the point on the graph corresponding to x of 2, x equals 2 is a point xy, which is the same as x f of x, which is 2 f of 2, which is 2 comma 7. So understanding this chain right here is conceptually important. You won't be tested on it, but it's really conceptually important that a point xy that's on the graph of a function is the same as x comma f of xy, because y is equal to f. And this particular point, where x is equal to 2, corresponds to the point on the graph 2 f of 2, which means the function f evaluated at x equals to 2, which we calculated right here to be 7. So using function notation. So we already know that f of x, so here's the other thing. We don't have to choose f. We can choose g of x, r of x, s of x, t of x, capital B of x. And we'll do so right down here. They all mean functions. So this is read f of x is equal to minus x squared plus 5x minus 3. And this is read g of x is equal to 2x plus 3. This indicates it's a function. This indicates it's a function. In each case, y is equal to f of x, y is equal to g of x. That doesn't change. So we want to evaluate f of 2. So here's the rule we're given. That f of x, this is our function rule, is equal to minus x squared plus 5x minus 3. And we're asked to find f of 2. Well, what you do is put 2 in for x and evaluate. Now remember, this negative sign right here deletes the number that comes next. And that's the number right here. So that's not the same as minus 2 squared. It's minus 2 squared. So this is equal to minus 2 squared is 4. 5 times 2 is 10 minus 3. So that's equal to minus 7 plus 10, which is the same thing as 10 minus 7, which is 3. So we have, okay, these are good examples. We have the next one here. F of Q. You're panicking because you don't know what to do. But all we do is we look at my function, and what did I do last time? Everywhere the symbol x appeared, I changed it to 2. But here, everywhere x appears, I'm going to replace that with q. Oh, so it wasn't so hard after all. Now let's do c, which is g of a plus 1. So g of x is equal to 2x plus 3. We want to find g. Our input value is a plus 1. So again, I replace x with a plus 1. So I'm multiplying 2 times x, so I have to put parentheses there, plus 3. Now I'm going to have to simplify. You have to simplify, use distribution. So that's equal to 2a plus 2 plus 3. So that's equal to 2a plus 5. Okay. Next concept, increasing and decreasing functions. So this is a very important technical definition. So let a comma b be an open interval. This concept of an open interval. An open interval does not contain its endpoints. Let's draw a little picture here. That's what you need to remember. An open interval does not contain its endpoints. So if this is A and this is B, then A is not included and B is not included, but everything in between is. So this is A comma B. It contains every number x greater than A but less than B. It does not contain A and B, and this is called an open interval. Especially those of you who are going to be going into calculus, it's a really important concept. Open intervals. In all of the mathematical discipline called analysis, open intervals are so crucial. So let A and B some open interval along the x-axis, like I just posted right here. And let f be a function defined over that open interval. That means every element x greater than A and less than B has to be in the domain of f. And suppose x1 and x2 are in that open interval. So in this case, I will say, here is my x1 and here is my x2. So I'm going to erase this right here because I'm going to use this as an example. Just know that our open interval, shrink, our open interval is A comma B. So we're just going to pretend like that's in the domain of our function. If we say f increases over the open interval whenever we have x1 less than x2, like I have in this picture, we have f of x1 less than f of x2. So I'm going to draw just some kind of a function. So here we have x1 and here we have x2, and these are the values. This is x, f of x1, and here we have x, f of x2. So here x1 is less than x2. Is f of x1 less than f of x2? Well, is this point lower, talking when going up and down, than this point? Then yes. But notice this has to happen for any choice of x1 less than s2, less than x2. So in this case, the function increases over the interval AB. This is not as hard. It's harder conceptually than it is visually. So let's look at another example. So instead of drawing something else, let's draw the easiest possible example. There's my function, that line right there. So let's find its value at x of 1. So this is f x, sorry, that's my value right here. And let's give myself some more room. So this point right here is x1 f of x1. And right here, this point right here is x2 f of x2. Is x1 always less than x2 whenever x1 is less than x2? Yes. So this is a decreasing function. You may be freaking out right now because I'm trying to explain something conceptually. When we look at it visually, it'll be really easy. So we say f is constant over the same open interval if for some constant c we have f of x is equal to c for every x over that open interval. So yeah, using open intervals and closed intervals, all of that is very reminiscent of calculus. I don't want you to be afraid to take calculus if it's in your study plan, but this is very calculus-like. So this would be a constant function, a straight line. So that would be constant. So let me just give you some more examples, okay? Actually, I'm going to draw these here. And literally, I'm just going to draw it's easier for me to draw these because for me to use GeoGebra, I have to know the corresponding algebraic expression. So let me just say our open interval, that's going to be A, and that's going to be B. So we're only dealing with areas between A and B. What I just wrote there is the interval between A and B. So let me do my first function. So there's its graph. Is it increasing or decreasing or constant over A and B? Well, we can see in some places it's decreasing. It might be constant right here for some areas. In some places over here it's increasing. So this is neither increasing, decreasing, or constant. So let's do another one. I'm not done with it yet, people, because that's not a function, is it? I'm going to erase some. I'm going to make it a function by erasing. Kind of like one of those things on Imgur, right? It's really satisfying to see. Maybe I'll post that on Imgur. Just me drawing a whole bunch of circles and making the eraser thing get really big and then erasing it. So let's find out where. There we go. So we're only dealing with this function from starting here over. But again, it's decreasing partially and increasing partially, so this is neither increasing or decreasing. What about something like this? I just don't have many options here, people. This would be increasing over a and b because it's always going up. That would be decreasing over the open interval AB because it's always going down. And the constant ones are the easiest functions of all. Constant functions are always horizontal lines. Okay. So now let's look at some examples. So here's the open interval. They want to know the open interval from -2 to -1. So right there's -2, right there's -1. This function is increasing. Now you don't care what happens at the endpoint because the endpoints don't matter. So this particular function right here over the interval -2 to -1 is increasing. From -1 to 1 it's also increasing. From 1 to infinity it's constant, and from here -infinity up to -3 it's decreasing. So decreasing from -3 to -2 it's decreasing. From -2 to -1 it's increasing. From -1 to 1 it's still increasing. And from all of these are open intervals now, and from 1 to infinity it's constant. So if it's constant from 1 to infinity, it's also constant from 1 to 8. Okay, that was it. That's that last part right there may have been a little bit, because again, I'm introducing your concept by purely abstract measures. There's one mathematical reasoning question I wanted to present to you. Did I erase that? Maybe it's on the next section. So that's it for 2.3.